Hey everybody, welcome back to Calculus Universalis. Today we wrap up Unit 7 with a powerful tool called Euler's method. This is how we approximate a solution curve to a different equation step by step, no solving required. It's a numerical method that shows up often on APFRQs. We'll walk through 1. What Euler method is, 2. How to use it step by step, and 3. How to handle it without or with a calculator. Let's get right into it. So what is Euler's method? If you know a starting point, x, y, not, if you know this starting point, you know a differential equation equals f of x, y, and you know a step size, h. If you know these three things, then you can perform Euler's method. It allows you to estimate the value of a solution at the next x value. So our formula is going to look something like this. If we have x of n plus 1 equals x of n plus h, and then y n plus 1 is going to be y of n plus h times f x to the n comma y sub n. When you use the slope from the differential at each step to estimate the next value, you can then solve this. So let's step into example 1. Our first example is going to be a differential of dy over dx equals x plus y. Starting point, 1, 2. Step size, h equals 0.1. Estimate y at x equals 1.1. So, our thing that we're trying to do is when x equals 1.1, what does y equal? That's what we need to get to. This is an h. So, compute the slope at 1, 2. F of 1, 2 equals 3. Right? Plug it into here. Then, plug it in and apply Euler's formula. So we have y equals y naught plus h times f of x, y naught, x naught, y naught, equals 2 plus 0.1 times 3, which equals 2.3. So what we did is we found our slope, we found our y value, we have our new y and our old y, and we solved for the new y. And so when we plug in x equals 1.1, we get y equals 2.3, and that is our final answer. So let's move on to example 2. Let's erase this here. Okay. So example number 2. If we have the same differential, dy over dx equals x plus y, step size h equals 0.5, we need to find y at x equals 1. So if we step from x equals 0 to x equals 0.5, we have f 0, 1 equals 1, y1 equals 1.5. And then our step 2 is going to be from 0.5 to 1. So if we do f of 0.5, 1, we have a 0.5 step size. Then we get 1. Plug this into our formula. We have 1 plus slope times y, which is 1.5. So we have 1.5, 1. So let's solve this last little portion from 0.5 to 1.5. It's going to be, add them together, and you get 2.5. Okay. So, example number 3, use Euler's table. So if we have a table of values, it'll make it a lot easier to follow. Something that looks like this, right? And you have your x net, y, and f of your values, and then your new y and your step size. Then you can easily follow Euler's formula by making your own table. So let's wrap up what we learned today. Euler's method is a numerical way to estimate solutions to differential equations. You move step to step by following y. Your next y value is your original y value plus your slope of the derivative times your f of your original values. So the smaller the step size h is, the more accurate the approximation is going to be. If you use a table to stay organized in the AP exam, it'll be a lot easier. And then lastly, some practice problems you can do are solving differentials in different ways, solving y minus x or dy over dx is 2x. And then start by practicing creating tables to estimate different values. So this is the end of Unit 7, Differential Equations. Amazing job. Up next is Unit 8, Applications of Integration, where you'll learn about volume of solids, accumulation in context, and more.